Uh, do you have my voice, right, Mr. Mr. Faris? My voice is clear, Mr.
Yes,
Abdul.
doctor, clear.
Yeah, thank you. Cheers. All right, let me start my presentation. Okay. Good morning, everybody. Last week, I began the class by introducing the concept of fault in power system with a particular focus on ambulance faults. So we discussed what faults are and how they occur and the various problems that they can create in electrical networks such as equipment damage, system instability and interruption in power supply. I also provided with some fundamental background information to help you understand the nature and significance of all of these disturbances. Okay, today I would like to continue our discussion with lecture 5, which focus on symmetrical components and ambulance faults. And in this lecture, I will explore how ambulance three-phase systems can be analyzed and by using the method of symmetrical components. This powerful analytical tool allows us to transform an unbalanced systems into three balanced sets of components, positive, negative, and zero sequence, which greatly simplifies the analysis of complex fault conditions. We will see later all of these sequences. By the end of this session, you should have a clear understanding how to apply symmetrical components to evaluate unbalanced faults and their impact on power systems. All right. This slide introduces the concept of fault currents in power system, which is a critical parameter in the analysis and design of electrical networks. And a fault current is the large current that follows when an abnormal condition occurs, such as a short circuit between phases and between a phase and ground. Under such conditions, the system impedance becomes very low and it will make a significant increase in current magnitude compared to normal operating conditions. Understanding fault current is essential for selecting and designing protective devices such as circuit breakers, relays, and fuses, as I told you before in my previous lectures. Okay, these devices must be capable of detecting and interrupting fault currents quickly to prevent equipment damage, maintain system stability, and ensure safety. So the magnitude of the fault current depends on such factors such as the system voltage, network configuration, and the equivalent impedance seen from the fault locations. Therefore, accurate calculation of fault current is a fundamental step in power system protection and planning. All right. This slide introduces the concept of balanced fault current calculations in power systems. In a balanced three-phase fault is a symmetrical fault that affects all three phases equally, meaning the system remains electrically balanced even during the fault conditions. Although such faults have a low probability of occurrence, they produce the maximum possible fault current, which makes them critically important for the design and rating of protective equipment such as circuit breakers, the fuses and so on. So because the system remains symmetrical, there is no need to use symmetrical component such as positive, negative, and zero sequences for analysis. So instead, the fault can be simplified and analyzed by using of single-phase Thevenin equivalent circuits, as you can see in the right-hand side of this slide. So this approach models the network as an equivalent voltage source and impedance and enabling straightforward calculation of the fault current under different balance conditions. Let me add a new student. All right. This in this slide, I want to explain how a balanced three-phase fault can be analyzed using a simplified equivalent circuit. From the fault location, the entire network is represented by a single phase Thevenin equivalent consisting of the Thevenin voltage. Uh, we can represent with V Thevenin, which represent the system voltage at the fault point, and Thevenin impedance Z Thevenin, uh, which which is representing the total network impedance up to that point. So because the system remains perfectly symmetrical during a balance fault, the analyze can only need to be carried out for one phase. And the behavior of other two phases will be identified, which significantly simplifies the calculation process while still providing accurate results for the fault current and system response. All right, this slide, let me add a new student, sorry. In this slide, I want to present the calculation of the balance fault current using the Thevenin equivalent model. In the simplified case, known as a solid fault, where the fault impedance is assumed to be zero, the fault current per phase can be determined by dividing the Thevenin voltage by the Thevenin impedance. So we have this equation. IF is equal to V Thevenin divided by Z Thevenin. So here, I Thevenin is representing the fault current in each phase. V Thevenin is the um, per fault phase voltage at the fault location, and Z Thevenin is the equivalent Thevenin impedance of the network up to that point. So because the system is balanced, this calculation applies equally to all three phases. This simple relationship highlights how the magnitude of the fault current is directly influenced by the system voltage and inversely proportional to the network impedance, making it a key factor in protection system design. All right, this slide also introduced the concept of unbalanced fault current calculations in power systems. Unlike balanced condition, unbalanced faults do not impact all three phases equally. Instead, they typically involve one or two phases, such as the in single line to ground or line to line or double line to ground faults. As a result, the three-phase current and voltages become unequal and disrupting the symmetry of the systems. We will discuss later. We will see this um, impact, and this deviation breaks the fundamental assumption of balanced three-phase operations, where quantities normally have equal magnitude and are separated by 120 degrees in phase. Consequently, specialized modeling techniques are required to analyze the network under these conditions um, and also accurately determine the fault current and system behaviors. So I explained all of this here. All right, this slide explains that why ambulance faults cannot be analyzed by using of a simplified single phase model. In contrast to balance faults, where the system can be reduced to an equivalent single phase Thevenin circuit, in unbalanced conditions require a more detailed approach because each phase behavior differently. So the symmetry introduced by such faults means that voltages and currents vary independently across the three phases, making a single phase representation inaccurate. So although direct three-phase analysis is possible, it is often complex and mathematically intensive, and it may not provide clear physical insight into the system behaviors. As a result, more advanced methods um, are typically can be used to simplify and better understand ambulance fault conditions. All right. Um, in this slide, I want to introduce the fundamental approach for modeling power system under ambulance fault conditions. So, since ambulance faults cannot be accurately um, analyzed by using of single phase models, the solution is to apply the method of symmetrical components. As a result, this technique transformed the original unbalanced three-phase systems into um, three separate balance networks. So we can use this concept here. So, and including the positive sequence, negative sequence, and zero sequence components. And uh, sorry, each of these sequences represent a specific pattern of phase relationships, allowing you to study complex fault conditions in a more structured and simplified way. And by decomposing the system into these balance components, the analyze can be become more manageable while still we can physically apply behavior of the original unbalanced networks in in our systems. All right. In this slide, um, sorry. In this slide, we want to introduce the concept of symmetrical components, which is a powerful method used to simplify the analysis of three-phase power system, as I told you, especially under unbalanced conditions. So the idea is to transfer the original three-phase voltages and current into three separate components: positive and sequence, negative sequence, and zero sequence. The positive sequence represent a balance systems with a normal phase order ABC, so similar to the balance of fault, and reflects a standard operating condition of the network. But in contrast, the negative sequence corresponds to the to a balance system with a reserve phase order ACD, and typically appears only during the unbalanced faults. And finally, the zero sequence consists of three components that are equal in magnitude and in phase with each other, and it is usually associated with grounding and natural path. So by decomposing an unbalanced system into these three symmetrical components, we can analyze complex faults more easily and understand how each sequence contributes to the overall behavior of the system. All right. In this slide, we sorry. In this slide, we wanna focus on how the Symmetrical components method simplifies the analysis of three-phase power system by decoupling the original networks into three independent models. So each of these models represent only one component, positive, negative, or zero sequence, which allows you to study their effects separately without the interface from the other components. This separation greatly reduced the complexity of analyzing unbalanced conditions such as faults in the systems, and because of its um, clarity, this model is widely applied in practical power system studies, including the fault analysis, protection studies, and also power quality assessments. All right, let me. Okay. In this slide, we wanna introduce the operator A, which is fundamental in the analysis of symmetrical components. The operator A represent a rotation of 120 degrees in the complex plane, and when a phasor is multiplied by A, it is rotated by 120 degrees, and when multiplied by A over 2, it is rotated by 240 degrees. So multiplying by I3 brings the phasor back to its original positions, and since a full 360-degree rotation results in no change in total. So an important property of this operator is that the sum of the three terms I plus A plus A2 is equal to 0, and this reflects a key characteristic of balanced three-phase systems where three phases of equal magnitude and 120-degree phase difference cancel each other when all of them are summed together. This concept is very essential for understanding how symmetrical components can be mathematically constructed and applied in power system analysis. Okay. The symmetrical components are, as I told you, a powerful method can be used in electrical engineering to simplify the analyze of unbalanced three-phase systems. And instead of dealing directly with unequal phase quantities, we can transform them into three balanced sets known as the positive sequence, negative sequence, and zero sequence components. So each of these components represent a specific type of system behavior. The positive sequence corresponds to normal balance operation. The negative sequence reflects phase reversal or asymmetric, and the zero sequence represent components that are in phase with each other. So by breaking a complex unbalanced system into these simpler balanced parts, you can analyze faults and stability and system performance more efficient and more effectively. So this concept can be especially important in the power system fault analysis, where it allows us to study different fault conditions in in a very manageable way. We can analyze them. All right. Okay. The first component is zero sequence. The zero sequence component represents conditions where all three-phase voltage or currents can be equal in magnitude and perfectly in phase with each other. In other word, VA is equal to VB and equal to VC, meaning that there is no phase difference between them. This situation typically rises during ground or air faults where the system becomes unbalanced and a common return pass through the ground or natural is involved. So an important characteristic of zero sequence current is that they can only uh, flow if such a return path exists. Without a natural or grounding path, this current cannot be circulated. So additionally, in power system with delta connected transformers, zero sequence components are continued and do not propagate through the network. So there is no any zero sequence. So to visualize this, you can imagine all three phases exactly on top of each other and completely overlapping, which clearly illustrates their identical magnitude and phase. All right, this is concept of the positive sequence component. In the positive sequence component is represented the normal operating condition of the three-phase power system where all three voltages or currents have equal magnitude and are separated by 120 degrees in the correct phase order and typically ABC. So this sequence reflects a perfectly balanced system, which is how power systems are ideally designed to operate. In this case, the rotating magnitude field produced is smooth and in the intended direction, ensuring efficient operation of equipment such as motors and generators. So because of uh, its models is a standard condition, the positive sequence network is often the primary focus in SDSS analysis, and it carries the ball power during the normal system operation, similar to balance fault systems. All right, this slide introduces the concept of negative sequence component in symmetrical components analysis. In this case, the three-phase quantities are still balanced in magnitude and separated by 120 degrees, but the key difference is that the phase sequence is reversed following the order ACB instead of the normal sequence. And this condition typically appears when the power system becomes unbalanced, such as during single phase faults or when uneven loads are present and we need to uh, uh, take into account negative sequence components in our models. And the negative sequence components is particularly important because it can have harmful effects on electrical machines. So it should be also considered in our model, and it can induce excessive heating in the rotor of generators and motors, leading to potential damage if not can be controlled in our system. So additionally, it will produce a reverse or negative torque, which opposite the normal rotations and can reduce efficiency or even cause mechanical stress. So therefore, understanding and detecting negative sequence components is crucial for protecting and maintaining the stability of power systems. All right. Um, this slide, sorry, this slide introduced the concept of the negative sequence component in the symmetrical component analysis. In this case, the three-phase quantities are still balanced in magnitude and separated by 120 degrees. And but the key difference is that um, the phase sequence is reverse, and we have to uh, the order is ACB. So um, and instead of the unnominal condition. So this condition typically we will have it during when we have the unbalanced conditions. All right. So this slide is showing that the fundamental idea of symmetrical components by showing how an unbalanced three-phase voltage systems can be decomposed into three balanced sets. So you can see that we will have the unbalanced voltages can be the combination of the zero sequence component, positive sequence, and negative sequence component. And on the left of hand side of this slide, we can start with the original unbalanced voltages, which do not have equal magnitudes or proper phase relationships, and these are then expresses as the sum of three distinct components, zero sequence, positive sequence, and negative sequence. These are then first we will have the zero sequence components, which all three phase voltages are equal in magnitude and in phase with each other. The second is the positive sequence component, which represent a perfectly balanced system with a normal phase order BC, ABC. And finally, the negative sequence component is also balanced in magnitude but has a reverse phase sequence ACB. And by breaking down an unbalanced system into these three components, you can analyze and understand system behavior more effectively, especially under fault or abnormal operating conditions. All right, let me have everything in the slide. So this slide builds on the concept of symmetrical components by presenting the mathematical representation of how an unbalanced three-phase system can be decomposed to the three components. So each phase voltage VA, VB, and VC can be expressed as the summation of the three components. The zero sequence, positive sequence, and negative sequence voltages, as you can see uh, in these figures, three figures, and specifically VA is equal to VA0 plus VA1 plus VA2, and similarly for VB and VC, you can see these equations. These formulations is showing that any unbalanced sets of phasors can be reconstructed by combining these three balanced sequences, and the zero sequence components are identical and in phase, and the positive sequence components follow the normal phase rotation, and the negative sequence components follow the reverse rotations. And this mathematical framework is can be extremely useful because it allows complex unbalanced condition to be analyzed in a structured and simplified way, which is essential for power system analysis, fault studies, and protection design. All right, let me have everything in the. All right. In this slide, I want to introduce the concept of symmetrical component, which is, as I told you, powerful method for analyzing unbalanced three-phase systems. The key idea is that any unbalanced set of voltages or currents can be decomposed into three balanced sets of phasors, zero positive and negative sequences, and each of these components is balanced and can be represented by a single phasor, simplifying analysis significantly. The zero sequence components are equal in magnitude and phase across all three phases. The positive sequence components represent a balanced system with the original phase order where each phase is shifted by 100 um, degrees in the forward direction. In contrast, the negative sequence components uh, um, also form a balanced set but with a reverse phase sequence. And importantly, here the point is that this composition applies not only to voltage but also we can apply it to current, making it a very useful tool in power system analysis, especially under fault or unbalanced conditions. So you can see all of these equations here. All right. In this slide, also, I want to examine the positive sequence components of three-phase system. These components represent a perfectly balanced set of phasors with a normal phase rotation, meaning the phases are separated by 100 degrees, as you can see in this phasor diagram, and follows the standard order ABC, and this one in this direction. And as shown in this slide, each phase has the same magnitude but is phase shift relative to the others. Mathematically, the reference phasor is V1 is equal to VA1, while the other phases are derived using the operator A, such that VB1 is equal to A2 V1 and VC1 is equal to A V1. So the positive sequence represent the normal operating condition of the power system and under a balance condition, similar to the balance condition, and it is the only component that present balance conditions, and this makes it especially important for standard system analysis, load flow studies, and understanding how the system behave under ideal conditions. So in the in this slide, I want to introduce the concept of negative sequence by phasor diagram and appropriate equations in the three-phase power systems. In this case, the three phasors are still balanced in magnitude, but as I told you, rotate in the opposite directions. We have ACB. So compared to the positive sequence. As shown in this slide, the phase order is reverse, meaning the reverse follows the ACB and instead of normal ABC format. So mathematically, the phase voltages are expressed using the operator A, where the relationship between the phasor is defined as VB2 is equal to AV2 V2 and VC2 is equal to A2 V2 with a VA2 is equal to V2. So this reversal in phase sequence is a key indicator of the system unbalance and typically rises during the unsymmetrical faults such as line to line or single line to ground faults and or single line to line faults. So understanding negative sequence component is very important because they can cause harmful effects in power system equipment, particularly in rotating machines like generators and motors where they induce additional heating and mechanical stress. Therefore, accurate analysis of negative sequence quantities is very essential for protection design and system stability assessment. All right, let me have everything in this slide. So this slide explain how phase A voltage can be expressed as a combination of symmetrical components in an unbalanced three-phase system. I just try to summarize everything in this slide. So in this unbalanced three-phase system, any phase quantity can be decomposed into three balance sets: zero sequence, positive sequence, and negative sequence components. As shown in this slide, the original unbalanced phasor is reconstructed by summing all of these three components. Mathematically, the phase A voltage is given by the sum of its components. VA is equal to VA0 plus VA1 plus VA2, and where VA0 represent the zero sequence component, and which is identical in all of three phases. VA1 is the positive sequence component and representing the normal balance system, and VA2 is the negative sequence component which reflects the unbalance in the systems. By defining VA0 is equal to V0, VA1 is equal to V1, and VA2 is equal to V2, we can simplify um, this expression to VA is equal to V0 plus V1 plus V2, and these formulations can be fundamentally used in power system analysis, especially for studying unsymmetrical faults, and as it allows a complex unbalanced system to be analyzed by using of three simpler balance networks. All right. In this slide, I want to extend the symmetrical components context to phase B. Similar to phase A, the voltage of phase B also can be expressed as the summation of its zero, positive, and negative sequence components. However, due to the phase shifts between the three phases, these components are related through the operator A, which represents a 120-degree rotation, as I told you before in the previous slides. The general expression is VB is equal to VB0 um, plus VB1 plus VB2, and here the zero sequence components remain the same across all phases, so VB0 is equal to V0. For the positive sequence components, phase B um, uh, lags phase A by 120 degrees by representing this formulation, giving the VB1 is equal to A2V1, and uh, other things is that for the negative sequence component, the phase rotation is reverse, resulting in VB2 is equal to AV2. And combining all of these three equations, we can obtain the compact expression VPB is equal to V0 plus A2V1 plus AV2. This formulation is very essential in fault analysis as it allows us to symmetrically reconstruct phase quantities from symmetrical components and better understand the behavior of unbalanced systems. Okay. Um, all right. This slide introduces a concept of fault current calculation in building on the previous analysis by using of Thevenin equivalent. So once the network has been simplified and the equivalent voltage and impedance are known, the fault current can be directly determined by using of basic circuit laws. As you can see, we can do everything similar to the other phases for phase C. So for phase C, we see zero sequence is equal to V0, VC1 is equal to AV1, and VC2 is equal to A2V2. So the combination of all of these components will be equal to VC is equal to V0 plus AV1 plus A2V1. So here we have um, all of these three equation. So in this slide, I want to explain how phase variables can be reconstructed from symmetrical components, which is a key concept in fault analysis of three-phase power systems. And instead of analyzing each phase directly, we can decompose the system into three balance sets: zero sequence, positive sequence, and a negative sequence component. As shown in this slide, each phase voltage is expressed as a combination of these components. For example, phasor A is simply the sum of three components, while phase B and C include the complex operator A, you can see in these equations, and which represent the 120-degree phase shifts. And this leads to the compact matrix from that relates phase voltages VA, VB, and VC to the symmetrical component V0, V1, and V2 by using of these matrices. So this transformation is very fundamental because it allows us to analyze unbalanced faults in a much simpler way by working in the symmetrical component domain and then converting the result back to actual phase conditions. So I want to give you a 10-minute breaks and I will back at 8. Okay? Please use the other link for the next lecture. All right? Is there any question?